The sun. It is a unique, clean and infinite source of free power, delivering more than 1000 kilowatt-hours per 1 square meter. 1000 kilowatt-hours is the amount of energy found in 100 liters of heating oil. Wouldn't it be wonderful if we could use the energy from the sun? Solar energy, wind power and water energy are forms of very clean energy generation that can be converted to, for example, light. Photovoltaic systems use solar cells to convert solar energy into electrical energy. Solar cells are usually made of silicon, that is a semiconductor material, which means that it can conduct electricity under some conditions but not others. When looking at the periodic table, we see that silicon is part of group 14 and is situated between aluminum and phosphorus. That being the case, a silicon atom has 2 electrons in its first shell. It has 8 electrons in the second shell, but it has only 4 electrons in its outer shell. The outermost electrons are called valence electrons and are of utmost importance because all silicon atoms consist of not more than 4 valence electrons. However, all of the silicon atoms will form bonds by sharing electrons to achieve a full outer shell with 8 electrons, which makes them very stable. In order to disturb the stable state, doping atoms are purposely inserted into the silicon. When boron is combined with silicon, free holes will be created because boron has only 3 electrons in its outer level. With 5 valence electrons, phosphorus creates additional free electrons. And that's where the magic happens. A solar cell consists of 2 silicon panels sandwiched together. One layer is doped with N-type dopants, the other is doped with P-type dopants. To allow an electrical flow of electrons, a front and a back contact are installed to the layers. Glass is installed on top of it to protect the layers and the electrical contacts from damage. Now it's time to take a closer look at the area between both layers. In the N-doped semiconductor, there is an axis of electrons. In the P-doped semiconductor, we observe positively charged electron holes. The electrons in one layer will find their corresponding free holes in the other layer. Consequently, an internal electrical field builds up at this transition that does not permit electrons and holes to jump into the other layer. However, if photons hit the silicon layers, electron-hole pairs will be created. If this happens in the electrical field, electrons are moved to the N-doped layer and holes are moved to the P-doped layer. The system will fall into a state of imbalance because of an excess of electrons in the N-doped layer. The corresponding holes can be found in the P-doped layer. It goes without saying that these free electrons and free holes try to combine. However, the electrical field does not allow such a condition. But if you connect the top layer to the other layer, for example by using a cable, you will see that electrons are traveling to the free holes. This flow is called an electrical current and can, for example, light a lamp. Solar panels can be installed on the ground or on your roof. The solar cells collect the rays of the sun and convert solar radiation into direct current, which is eventually converted into more usable alternating current by a piece of equipment called an inverter. Connected to the inverter is another device that is going to measure the electricity produced by the photovoltaic system. Generated electricity may then be reimbursed by your electricity supplier.